you sort of thought that we as a civilization had gotten out of this idea of that we're going to throw something, we're going to pollute something into the atmosphere without really knowing the consequences. You would have thought we had gotten to the point where, like, if we're going to do this, let's think through the consequences first. This is a classic example that we really haven't learned that much. We just went back to throwing it into the atmosphere and then, kind of waiting to see what the effect is.
Greetings. I'm Yvonne, Stat for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations, produced today through WGBH4 Network's webinar. As satellites accumulate in Earth's orbit, scientists are increasingly concerned about space debris, not just from those huge chunks that fall from the sky and we hear about, but especially the particle residue from small satellites and other objects as they burn up in the high atmosphere. The chemical contents of that particular dust may impact both the ozone layer and the climate. Our guest today is one of the leading scientists investigating this particle dust and its potential effects. Dan Cziczo is professor of atmospheric science at Purdue University. His expertise is in the atmospheric particles and cloud formation, essential components of climate. He will explain for us why the analysis of this space debris is so important and how atmospheric scientists determine the potential threat to the ozone and the Earth's climate. Dr. Cziczo, welcome and thank you very much for joining us today.
Fawn, thank you for having me back, and it's wonderful to see you again.
And so we'll just start right in here on this space debris. What kinds of satellites are we talking about? Because we usually think of these gigantic things that you hear about falling in your backyard and stuff like that. What are we really talking about here?
Yeah, it's a great question to start us off with, because I think this is where there's some misconception. And so what we worry about as humans to a great extent is material striking the ground or striking an aircraft or something like that. And so when we think about deorbiting satellites, we often think about the risk that it could pose to, hitting a home or hitting an individual, hitting a plane that's flying or something like that. And so we're actually not talking about that material. We're not talking about, pieces of material or satellites that are large enough to hit the surface of the planet. We're actually talking about things on the smaller side, or things that would come off of that spacecraft as it enters the atmosphere. It strikes enough atmospheric thickness, enough atmospheric density at about 100 kilometers, about 60 miles, that it starts to burn up. And so I think we're all familiar with this. We look up in the night sky, we see a shooting star. It's the same physics of what's going on. But these spacecraft, especially the smaller ones, burn up at that sort of 100-kilometer level. And then that material is basically, we say, ablated, left behind in the upper atmosphere. It is not the material that you just alluded to, the stuff that actually strikes the surface, a chunk of material that could pose a threat.
And about how big are those satellites that we're talking about, and how many? And these, I think the predominant ones are the Starlink ones from Elon Musk's crowd, but there are others waiting to join. So how big are they and how many?
Yeah, no, it's another great question. So it isn't a matter of just how big are they. It's a matter of, what happens to that satellite. So you're right. It's the satellites that tend to be on the smaller side that might, using this word again, ablate completely or burn up completely. Yeah. So you sort of think of these newer generations of sats, these sort of CubeSats, the bread basket sort of size ones. Those are certainly large players in this. And so when we think of Starlink and things like this, these constellations of small satellites, those are big players. Larger material, the upper stage of rockets, larger satellites also burn up. They just may not burn up completely. And so some part of their superstructure, some part of even the larger material is left behind in the atmosphere as well. And so it's sort of, some fraction of the large stuff, and then probably a complete part of the smaller stuff. And then another part that factors in is, how they're re-entered into the atmosphere. So like what velocity they come in, what's their angle that they come into the atmosphere. And this kind of dictates how much burns up. And so, of course, if you're concerned about this material not making it to the surface, you might want to burn up as much of it in the atmosphere or make the residual amount as small as possible. And so this is, I think, something that we'll continue to elaborate on. But, if you're only concerned about material not hitting the surface, then what you are doing is you're burning it up and you're leaving it in the atmosphere. And so this is the trade-off that, we as a civilization have to start thinking about.
Right. And at the present time, there are thousands of these. For the Starlink is the predominant one, I think now, and they're maybe small car size or smaller even or whatever. But there are thousands of them up there now. And I thought that originally they thought it was a good idea if they burn up there when at the end of their lifetime. And I'm not sure what the lifetime is. I've seen different figures, 25 years, but I think it's less. And so that they burn up there, but there are thousands at this time. It was 15,000, something like that. But they're projecting. Do you know how many in like just even a few years?
Yeah, I'm going to try to answer the first part of what you
Yeah.
were asking about first, and then we can come back to sort of the numbers that we think we're going to be dealing with. So one of the problems is that what we call low Earth orbit, or LEO, LEO, is the common name of it, is becoming a very crowded and therefore a very dangerous place. So the viewers and the listeners can sort of think about a highway system, and that there's a lot of cars out, and your chances of crashing into another one become greater because there's just much less separation between them. So one of the things that's going on right now is that people are starting to think about, well, how do we clear out this low Earth orbit, this LEO, because we want to put more satellites up. We want to space, and we want to get rid of things that are defunct, that have failed. We might want to get rid of older technologies and update them with newer technologies. And so that's part of the problem, is we're actively trying to clean this area out. And some of the folks that are listening might have heard, some of these terms like design for demise, this idea that you put a satellite up, but you have a plan for getting rid of it, something that we didn't really think about in, the 50s, the 60s, the 70s, as we started putting material up. It seemed like there was infinite space up there. And now we're getting to the point where we're realizing it's really quite crowded. And so, separate from the increase in numbers, clearing out low Earth orbit makes perfect sense, and people have thought about a couple things. One is the idea of a parking orbit, that you move this stuff to some place that it's not going to interfere with the area that you want your satellites in. That's one idea. The one that has proven to probably be more cheap and that people are using more is to just deorbit this, which again leads to this ablation in the atmosphere or striking the planet and causing problems. So I just wanted to point that out, that's where we're coming from. That's one of the problems that we have to solve. You're bringing up, as your second point, something that is really important, which is we're moving into an age where we're not just replacing satellites that are there. It's not sort of a one-for-one replacement. When we think of something like Starlink, we're talking about, tens of thousands of satellites, and their size may be small, their mass may be small, but they're not expected to live really long. This is not something like you're putting these up for, many decades and they're going to keep performing. The idea is almost that these things are disposable in a way, where you put them up and then you intentionally deorbit them and then you replace them and you put them up. And it's not just Starlink, don't get me wrong. I mean, there's many other, there's a European constellation that's been proposed. I believe that there's a Kuiper, which is a Bezos project. So it's not one individual. It's certainly a large number of things, and it's largely for communication. Things like GPS. Starlink, of course, is supposed to link folks' internet. So there's reasons that we want to do this, but I'm not sure that we've fully thought through all of the consequences at the same time, because just simply deorbiting material doesn't mean that it goes away. And I think that's what we're going to talk more about too.
Exactly. And that's absolutely the next question. Now we've got the stuff they're burning up. This is in the upper atmosphere, right? And if you'll take us through that, that debris is a matter of concern now. And so I'm going to ask you if you'll explain what this is, because you've been cited a million times now with that study of yours for almost 2 years ago now that has gotten so much attention. So if you'll explain that for us.
Yeah, no, thank you for the lead into this. So, maybe I'll even take one step back of how I became involved in this, and just sort of talk through this, because I think there's an interesting sort of history here, which is when I first started working in the upper atmosphere. So again, just to remind the viewers and the listeners, the lower part of the atmosphere, the part that we live in, is called the troposphere. The next layer up, and I think everybody has seen this, in a high school science class, that there's these layers. It's sort of a layer cake. The next layer up is the stratosphere. That's where the ozone layer is, something that we'll talk about. And then above that is the mesosphere. And the mesosphere is where some of this action is going on that we're talking about. So that spans this sort of 80 to 100-kilometer part, where when spacecraft come in, they experience that atmospheric density we talked about, and they start to burn up to ablate. So when I first started studying this, 20 years ago, you can see all the gray hair, so this is early in my career. We were looking at meteoritic material, meteorites burning up. And so again, if you go out on a clear night and you see those shooting stars, by and large, that's natural material, that's meteoritic material. And this has been going on forever. And so that it's quite interesting because, these burn up in that same location in the atmosphere, and this is natural material that then condenses back together in this layer, and then it falls out. And so we are able to fly aircraft in the stratosphere, the next layer down. And really, for decades now, we've known that this meteoritic material comes in, burns up, recondenses, falls out. We can sample those particles and we can look at their atmospheric effects. And so again, totally natural, something we've been studying now for decades. What's quite interesting, and I think this is why you're having me on today, is that Dan Murphy, one of my colleagues at the National Oceanic and Atmospheric Administration, and our group at roughly the same point in time were flying in the stratosphere on different aircraft. And we started to realize that these meteoritic, these natural particles did not look the same as they did a couple decades ago, that they looked like they had different ratios of components, so different components in them, or the ratios of the metals. And I think we all know meteors are not changing in composition over decades. And so something else had to be happening. And sort of the aha moment was, well, this is probably a spacecraft signature. And so this had been theorized for a while. People had said, this stuff is burning up and it must be going through the same cycle in the atmosphere. But, you can kind of think in the 1950s, when there's a few, satellites coming back into the atmosphere every year, 60s, a few more, and so on. This wasn't a big deal, and it was very hard to see that signal. And so this is that standard, the signal had not moved out of the noise yet. And so it was, 2022, 2023 that we started to realize that, you're seeing enhancements of aluminum. You're seeing enhancements of lithium. And what are most spacecraft built out of? They're built out of, sort of aluminum, and lithium is part of those alloys and part of the batteries and things like that. And then there's lesser trace materials that you wouldn't find in meteors. And so now these sort of natural historic particles from meteors that were coming down actually have a fraction of them that are due to spacecraft material. So I hope that gets at the question that you were asking, but certainly I'm happy to follow up. We can start to talk about some of the implications or dive
Yes.
a little deeper into this, whatever you like.
Yeah, no, really, the two things there, that how you were able to distinguish this is not meteor dust here, and more of this is that then you're concerned about that, Ash. You're the expert on clouds, and that starts with these little things called aerosols, and you need particles to do that, and that's where your expertise is important, I think. So what is the concern there for the cloud formation that from this residue, from this dust?
Yeah, I'm going to again circle back. I'll answer the first part of what you asked, and then we can move on to the impact or the potential impact. So you're absolutely right. So what we do in the atmosphere, what we're able to do on these aircraft is it's a technique called single particle mass spectrometry. And so we're bringing in these little particles. And so folks have to imagine, if you pull out a human hair, that hair is about 50 microns in diameter. And these particles are like a micron or less in diameter. So you're talking about, invisible to our eye particles, a 50th or less of a human hair in diameter, but they're in the atmosphere all around us all of the time. And so our techniques are able to bring those in one at a time and chemically fingerprint them. And that's how we could tell that this was no longer the natural material that we had been seeing, but that there were new and different components or different ratios of components in them. So I just wanted to sort of give that background of that's how we're doing it. Now, the really interesting question is the second part, which is, what is the atmospheric impact? And I'm going to be a terrible scientist right now because I'm going to tell you we don't know yet. And that's a bit maddening. And I'll tell you why that's a bit maddening is that, so first off, we can theorize what impact this material could have on the atmosphere. And let's run through a few of those things. So we know this material is burning up in the mesosphere at that sort of 100-kilometer level we talked about. And so it's being sort of ripped apart. You can sort of think of this high temperature ablation process, and then it sort of recondenses, and you can sort of think about soot recondensing out of a fire or out of an engine or something like that. Well, the same thing's happening, but instead of carbon that you find in soot, it's recondensing out of these metals that the spacecraft and the meteors were made out of. And then those small particles are then falling out of the atmosphere, and they're sort of interacting with the other things that are in the atmosphere. They're picking up some material and they're coagulating together. And then we see them as they fall out of the atmosphere. And this whole fallout process takes a couple of years. The atmosphere itself is sort of sloshing around, and it's sort of falling down over the poles and then moving back and forth during the summertime. And so it's not quick. And they do age a lot in the atmosphere. And this is actually something we worry about, which is that as they sort of move around and fall down, they're falling through the ozone layer. And so as the title of what we're talking about today implies, that is one of the things that we are most concerned about, is because whenever we put new material through the ozone layer, we have a chance of adversely impacting that layer. And so for the listeners and the viewers today, one of the classic things that we always think about as atmospheric scientists is when we were putting a lot of these chlorofluorocarbons into the atmosphere, which was supposed to be completely inert. We didn't need to worry about them. But as they made their way up into the stratosphere, they were starting to break down. And in fact, some of the components of that material led to this loss of ozone. And so that's one of the things that we're really worried about and that we have to do in the laboratory. We're trying to do that right now, which is to sort of look at this material, look at how it might impact that ozone layer, that, could it be a surface that chemistry goes on that's adverse to the ozone layer? And so that's one thing that we really need to find out about. Another thing that we know that particles in the upper atmosphere do is that they're the seeds on which clouds form. And so this sounds relatively harmless, like, oh, you've got some more seeds that clouds form on. One of the problems is that clouds that occur both in the stratosphere as well as the upper troposphere can have adverse chemical as well as climatic impacts. So chemical first. If you form more clouds in the stratosphere, those are the sites that ozone can be depleted on. And so even if the particulate was chemically inert, if you're forming a lot more surface area, that surface area could itself lead to ozone loss in sort of the classic way with the residual CFC, chlorofluorocarbon material. So that's another thing we have to figure out is this material capable of forming those clouds? And then if it is, can it form clouds as it falls even further into the atmosphere, into the troposphere, the part we live in? Because those clouds can trap heat. And now that's the climate part of this equation, which is if you start trapping more heat, you start tending to make global warming even worse from a different source. It's not putting greenhouse gases into the atmosphere anymore. It's could these particles that are coming back into the atmosphere from spacecraft actually also be a player in that warming? So I just said a lot there. That's probably a lot to digest. But you'll get the idea that there are a lot of implications that this material could have. We haven't even talked about all of the ones that have been theorized, but we simply don't know yet. And this is the frightening part as a scientist, is that, you sort of thought that we as a civilization had gotten out of this idea of that we're going to throw something, we're going to pollute something into the atmosphere without really knowing the consequences. You would have thought we had gotten to the point where, like, if we're going to do this, let's think through the consequences first. This is a classic example that we really haven't learned that much. We just went back to throwing it into the atmosphere and then, kind of waiting to see what the effect is. And so, yeah, that's a little terrifying as a scientist, I'll be honest.
Yes, I'm sure that it is. And there is another thing here. You remember with the chlorofluorocarbons, they were able to sort of address that. It's not finished yet. The ozone layer has not completely healed, but we just removed those, stopped using those, and we saw a fix, so to speak. But that is not clear here, at least to us mortals, like, what can you do with this stuff? You're saying that we don't know yet. We need some more work on this. But at the same time, we have this problem of, well, what are they going to do with it? And they haven't gotten to that. Can they do something? Can you scoop it up or something? Or
Yeah, I really like where you're going with this question, because this is sort of like, how would we design the term
yeah,
that a lot of people use now is design for demise. Like, we know that we have to demise these
yeah,
spacecraft. How do
right.
we design for it properly? And so there are a lot of ideas, and there's a lot of people smarter than I am thinking about this. So I can kind of run you through what people have talked about. We mentioned earlier this idea of a parking orbit. Until we know what the atmospheric impact is, the question would be, can you park this material somewhere? Can you park these sort of defunct spacecraft somewhere that you're not entering them back into the atmosphere, but they're also out of the way of the new things that you want to put into this low Earth orbit? So that's one idea. I think the reason that people have tended to not do that is that there's a cost associated with that.
Mhm.
You have to maintain the fuel on these spacecraft. You have to park them in that orbit before they completely break down. So there's a lot of reasons that people don't want to do that. On the other hand, if you just crash this through the atmosphere and burn it up, there's this seductive idea that it just goes away, and that poof, it burned up. It's fine. I don't have to worry about it anymore. And so I think that's what I think folks have been struggling with. Now, as scientists, I think you're getting at one of the interesting things, which is, can we figure out, is there a part of that satellite? And I'm just making this up, but is there a single component of that satellite, a single material that's used on that satellite, which could be responsible for a problem in the atmosphere? And then could we work with the spacecraft engineers to think about, is there a way to engineer around that component or around that material? And so, if you sort of think about component X is responsible for ozone loss, can you find a way to not put component X up? This is very much like those CFCs we talked about, where we found replacement technologies that didn't have the same properties that were leading to ozone loss. Now, what's scary about this again is that we are just coming out of the CFC ozone hole 1980s, 1990s era. You would have thought that we would have started thinking about this before we started deorbiting the material. And that's the problem, is that, we probably really should have been running these experiments in the lab. We should have been funded to do this before we started to deorbit the spacecraft. And so we're kind of putting the wagon before the horse again, which is, we're doing it. We don't know what the consequence is. We're trying to figure that out. And then when we sort of uncover a problem, then we got to go back and figure out what the solution to it is. And again, that's the maddening part, is just not sort of, learning from history and allowing it to, again, repeat itself.
Right. And in our last 5 or so minutes here, this brings us to the fact that your research has been shut down recently, right? So I believe there were a couple of more studies that were in line here to go after this problem exactly, and it has now been shut down. Can you give us any great explanation of why that should happen?
I mean, the simple answer is no. I can't give you a real explanation. But I can go into a little bit more detail on this just
Yes.
to make sure that people understand. So I think there's really two problems. The overarching problem here is that research in the United States, the research that we do through federal agencies, the National Science Foundation, National Aeronautics and Space Administration, NASA, NOAA, I mentioned earlier, National Oceanic and Atmospheric Administration, Department of Energy, we could go on and on, Environmental Protection Agency, and so on. Those are the big players in our field. Of course, folks that are in health are thinking about National Institutes of Health, things like that. So I'm trying to keep this as the chunk that would fund this research. Those funding mechanisms have been cut or completely wiped out. And so, just using NASA as an example, the standard annual call for proposals to do research, which should have come out early this year, February, just has not come out.
Mhm.
And so, how do we do really important research, which is really timely and something that we need to do right now, and in a climate where that funding is being taken away? And the simple answer is we can't. So we try to find novel ways to fund these things. Maybe we go to private entities, but it's really not a replacement. The thing that led the U.S. to become the scientific powerhouse, the scientific center of the world, has really gone away this year. But then I think you're also speaking specifically about this research, because this research in spacecraft effects on the atmosphere, which was largely done through our colleagues at NOAA, but also at NASA, has largely been shut down, and we don't really have any answer to why that would be the case. Now there is a healthy amount of research going on in Europe. But we can also sort of think through that the big players in putting a lot of these new spacecraft up are in the United States. We mentioned who they were before. And that's a big problem. So, I mean, if we're putting up this material, if our country's putting up this material, you would think that we have a responsibility to figure out what that effect is and how that is going to affect not only our country, but really the global atmosphere. And we've simply dropped the ball in the last year on that. And so I think that's something that we really have to take a long, hard look in the mirror. Is this really what we want to be doing as a country or not? I don't think it is. I mean, you would have thought 100 years ago we got out of the business of throwing pollution into waterways and things like that. Now we're polluting the upper atmosphere in a very different way, but it doesn't make any sense.
Right. Well, the other part of that is that it affects the whole globe. So there's, in a sense, we have a responsibility. And as you say, most of this is centered in the United States. Most of these satellites at present are from the United States, and just one or two companies, really. And to have it shut off like this, the research shut off, is really kind of dangerous, maybe. But the other thing, very quickly before we close, is it possible, given what information you do have, to model and project from what you have, or is that impossible?
No, that's another excellent question. So certainly there are some models that are capable of looking at these layers of the atmosphere. Most of the weather models we deal with are the troposphere where we live, rightly so. Models become, there are less and less models as we move up and up in the atmosphere, just because it sort of gets away from us as humans. And so we kind of drop the importance, but there are very capable models of doing that. And they are only now in the last couple of years starting to think about things like spacecraft emissions from rockets going up, but also this material coming back down. Now, here's the scary part, Yvonne, because models are only as good as the data that we have available to us. And so we can build models, but if it's unconstrained by atmospheric measurements, if it's unconstrained by, trying to understand how these spacecraft are burning up as they come back in, then you have to ask yourself, how good is that model at all? And that's, again, going back to the contemporary research. If we don't have research flights going on, we're not doing tests on this material, if we're not considering how it's burning up, what chemical impact it can have, we really don't have a chance of helping inform those modelers of how to build their model correctly.
Right. I understand. Well, leaving on that cheery note here, this is really serious. I hope that people will be able to understand it, because we get almost nothing from media. So I thank you very much for giving us this wonderful information. It's very, very helpful. And I hope you'll find a way to continue your work. It's very valuable. And I think now we'll just move to the questions, if that's okay. Um, the first thing is that I see is that it's not just a US problem. I think maybe that other countries are launching. Yes, if we could go into that, launching, I guess, these satellites. And is there, how do you get all these nations to cooperate as for solutions to those problems?
Yeah, that's an excellent question. And there's some scary similarities here with what we talked about before, which is this chlorofluorocarbon world, also a climate change, global warming world, where certainly there is no one country that's responsible for it. At this time, a lot of the mass that is going up, a lot of the material that we're discussing is coming from the United States. And again, we're sort of thinking about the developing world putting things up and the developing world being responsible for what's coming down. It's not so much the developing world. And so we have to acknowledge that. But certainly this is something that is going to have to take a global effort to think about this. Who are the players in space? Who's putting this material up? How do we sort of differentiate? How do we, think about the responsibility of figuring this out? And certainly it's going to take a multinational agency, a United Nations kind of effort, which is where we see things like the Intergovernmental Panel on Climate Change, again, as an intergovernmental agency. But if you're ignoring it, if one country is ignoring it, then that takes that player out of the system and it makes it that much less potent to do that. And of course, at this point, if we are the major player responsible for this and we're not acknowledging that, we're kind of sloughing our responsibility off on Europe. That is a big problem.
Yes, and I just want to add there, I don't know if we've mentioned how many are expected, say, within the next 5 years, but of these satellites, these small satellite constellations, I think it's around 60,000 will be up in that atmosphere. It's a pain in the neck for everybody, and the idea is you're going to spread the internet, not internationally, do all these good things. There are all these other reasons for it, but it is mainly from this country at the moment. But as you say, the next question is, see, why has the issue of space debris been neglected by the media, except for the large debris?
Yeah, that's another great question. Certainly since this paper came out, and again, I just want to acknowledge Dan Murphy, who is the lead author on that paper. I think everybody really on that paper has tried to do a lot of media outreach, and thank you for giving us a platform right here. We really appreciate it. So I think it's been picked up. I think you see some of the media outlets picking this up. Certainly folks that are interested in space and things like that. And so you'll see it get picked up from time to time. I know this idea that we could be doing something that would adversely impact the ozone hole certainly has been picked up a few times. But yeah, I think it's a great question. I don't know why it hasn't resonated. It might be this idea that we don't have this definitive, we are doing this yet. It's more like, hey, why are we putting material there that could have these deleterious effects without understanding it? And that might not be, as sort of interesting, or that might not have that sort of hook for people quite yet. It's sort of like we're raising the alarm, but we don't quite know what effect it's going to have yet. When the polar ozone hole had already formed, and you could see, this loss of ozone, that really captured people, and this time we don't want to get to that point right before we start to do something. We want to learn from our past mistakes, but I'm not sure that it's got that media resonance. So I think that's a very good question, and I'm afraid I just don't know the sort of psychology of the answer to that.
Yeah, and it's a very concerning thing, really, because you may get to that point and it's not clear that you can reverse it. So in any case, here's another one. Why are so many satellites being deployed when overcrowding is such an issue? And it is an issue mentioned for astronomers too, by the way. Yeah.
Oh yeah, no, that's a great point. Is I think for astronomy, this idea of light pollution and interference is a big deal, and I'm not qualified to speak to that. You have somebody much smarter than me come on and talk about it. I think there's a variety of reasons. There's more players in the game. there's more people in space. Certainly it didn't used to be that, sort of private companies were capable of putting material up. So there's more players. That's one thing. The other thing is that, in a lot of these cases, like, for communication purposes or internet purposes from orbit, you're talking about coverage. And so instead of having, one satellite up, people probably remember the old days where we had a handheld GPS and you had to link up to 3 or 4 satellites or whatever it was. People want that connectivity. And what does that mean? It means that you have to have more stuff up so that you're able to sort of line of sight, see that and have that communication ability. And so, people think about these constellations where they can see this sort of, this sort of string of pearls, as it's been called, moving across the sky. Well, that's to allow you to always have communication. And that means more material, more satellites that have to be up. And if you're trying to do it and your friend's trying to do it and this country's trying to do it, it doesn't mean that it's just one constellation of satellites. Now everybody's got their own constellation. And so you get this multiplication. So.
And the big problem. Okay. And here, it's a little more technical. How do scientists monitor and analyze that ash debris in the atmosphere?
Yeah, another great question. So this is part of the funding issue that we're going through. So to date, we rely on research flights, and there's no university in the US that can operate and afford a stratospheric research aircraft. So we are dependent on agencies like NASA, NOAA, the National Center for Atmospheric Research, larger groups that can have capable aircraft. And then we would have, hopefully in a good funding climate, annual measurement campaigns where we're going up. And so that's what we've been using for these data. Unfortunately, for budgetary reasons, these missions were getting further and further apart in time. So instead of maybe doing them every season or something like that, you might have been doing them every couple of years. And now, we don't really know what the prospects are in, say, a 2026, 2027 for getting any data. There could just be gaps of data. And so if there are large changes, like we think there are going to be in the number of satellites and the number of deorbits, we are not going to see that. We will be blind to it. There are some ground-based assets that can see things like, these burn-up streaks that are going on, but it's not the same as getting that what we would call in situ data or data that's in place, the actual material in the atmosphere. And so, we kind of have to use these modeling tools that you alluded to earlier, maybe some ground-based optical instruments, things like that. But we are certainly losing out by not having the actual information from the atmosphere.
Okay, thank you on that. Now, a couple of these that I see on the list of things you've addressed already, but it's good to sort of mention them again. Does the satellite ash or particles, does that differ chemically from meteorite ash?
Yeah, this reminds me of something I tell my students all the time. Repetition is the key to learning.
Well,
so,
it's absolutely essential with this technical stuff, so it's good.
Yeah, no, we should all be prepared to ask the same question until it really resonates with us. So no. So again, a great question. So yes, there's a chemical fingerprinting. The technique that we do is called single particle mass spectrometry. So one particle at a time. We actually strike it with a laser that allows us to liberate the material from the particle, create ions, and then we measure those ions. And so this allows us to chemically fingerprint. And so this is something that we discussed in that paper that you alluded to. But the chemical fingerprint of this spacecraft material is unlike anything else that we've seen. It is really distinct. It doesn't look like a meteor or something like that. And we can actually match it up with the components that we know are in spacecraft. So the aluminum sort of frame superstructure, the lithium that's used to lightweight that aluminum, some trace components that we know are in spacecraft, things like that, precious metals which are used in electronics. So we're really able to discern that material came from spacecraft, sort of unequivocally say this was from spacecraft. It wasn't from a natural source.
Okay, and then here again, I think you addressed it, but it's we need to hear it again anyway. How long does it take for the debris ash to descend through the atmosphere levels and then doesn't go all the way down? I think anyway, go ahead.
Yeah, no, no, no. Again, it's worth kind of going over this because I
Yes,
said it
yeah.
rather quickly. One thing that we should keep in mind, though, is that these are very small particles. You remember we talked about these being sort of submicron particles, and so we have to get out of the mindset they don't fall out of the atmosphere
Mhm.
gravitationally. It's not like dropping a bowling ball out of an airplane and it's going to go down. This stuff basically is going to more or less float there. Its gravitational settling velocity is very slow. And so what we actually rely on is that the atmosphere sort of sloshes towards the wintertime pole and then sort of falls down and then sloshes back towards the equator during summer, and it moves down. And as it's doing that motion, that dynamics, it's actually falling. And so that fall sort of process takes a couple years. So when you have something burn up in the mesosphere and form a small particle, it doesn't come down in a day or a couple of days. It actually hangs around in the mesosphere and the stratosphere for maybe a year, over a year each, before it makes its way out of the atmosphere. And then once it makes it to the troposphere, where we are, everybody can say, well, we have clouds, we have rain here, and so it gets washed out pretty quickly or can fall out pretty quickly. And that process can speed up a lot. So you can fall out of the troposphere in days or weeks. But these particles tend to sit in the upper atmosphere for a long time. And that's a little bit scary, that because that means that, even if we sort of stopped burning up this material tomorrow, it would still be years before it found its way. It sort of flushed out of the atmosphere. And so any effect it's having on chemistry or cloud formation is going to be there for a while.
Right. And this one, it goes like with this too, is there a way to collect that ash or whatever, or eliminate it? And you addressed it before, but if you would again, then.
Yeah, no, no, no. So elimination is really hard once it's burned up because it's formed all of these small particles. And so we can use this analogy we talked about before with respect to a fire. It's a lot easier to not start the fire, not burn up that log. But once you've burned it up, it's smoke and gas, and actually collecting that material after the fact is extremely difficult. I'd say probably impossible. And so, in terms of collecting this material, you don't want to try to do it in the atmosphere after the ablation has taken place. I don't even know how you would do that because
Mhm.
there's natural material there that you wouldn't probably want to sweep up. You want that to remain. And so this idea of before you burn the spacecraft up, parking it, or bringing it down in some other way, or having that material be inert in an atmospheric sense is really what we want to do. And I think that's where a lot of these design efforts are going.
Okay. And one last one, can the satellite ash disturb the Earth's magnetic field?
Oh, this is an interesting question. I know
Yeah.
that there's been a few folks that have suggested this in the past. I'm afraid this is far outside of my area of
Okay, yeah.
expertise, and I just don't know. Again, there are these natural metal ion layers from meteorites that are in the
Yeah,
Earth's
yeah.
atmosphere. And so, the perturbation that we're talking about now is that, maybe on the order of 10% of this material is from spacecraft now. And so what we're doing is relatively small. What I think we're worried about, and maybe the answer to the question is that, if we fast forward some decades into the future, there's going to be a crossover point if we keep going the way we're going, where there's more human material, anthropogenic material coming in
Mhm,
than spacecraft material. And I simply don't know the answer. Like,
mhm.
do all those new metals in the atmosphere, could they have an impact? I'm afraid I just don't know.
Yeah, right. It doesn't add up into the cloud situation or anything like that. But
Yeah.
I sure hope that you are going to be able to recover your research here. This is really important. Thank you for your many years of dedication. This is a very interesting area for you too, I am sure. But in any case, thank you again. Good luck. And I do hope that this problem will be resolved. Thank you, Dr. Cziczo.
Fun. Thank you so much for having me on again. I really enjoyed this conversation. And
Yeah.
yeah, thank you again. It was a pleasure.